So could you please give it up in the customary fashion of banging your hands together loudly for Dr. Sabin.
All right. So before we begin, I'd like to, again, for us kind of to situate ourselves in time and space. We're floating on this beautiful blue planet, and we're here on Gadigal land. So I'd like to pay my respects to the elders past, present, and emerging of the Gadigal people of the Eora Nation. And recognize again that this has been a place of learning and knowledge exchange for tens of thousands of years. And of course, geoscience and geology explains how our first Australians arrived in this country, of course, because of sea level changes that were affected by orbital cycles. So 80,000 years ago and 20,000 years ago, we had glacial maxima, and so sea levels were much lower, and it then exposed more land bridges that first Australians could use to get across from Southeast Asia into Australia. So anyway, we're very, very fortunate to be here. So yesterday we started talking about this idea of whole Earth modeling, and I agree with you, Chris. It's like, well, can we really do it? We're trying. We touched on this idea of open source community science, right? Being able to create tools that are usable by the whole community. But today, let's delve under the hood of this beautiful planet that we have. What makes it very special is that, of course, we have wonderful folks like you around, and that's mostly thanks to carbon, okay? Carbon, you might say, is not that extraordinary as an element, but of course, we are carbon-based organisms. I'm going to try to see if I can reduce this echo by turning off the other microphones, folks. Just give me a sec. I'm not really sure.
I'll see what I can do. I think I've turned off most of them.
You have. Let's see. I don't know if that helps. No, not really. That's okay. Okay. So, of course, we're carbon-based organisms, but also we've got carbon-rich rocks. That could be coal, but it can be also diamond, and people seem to like both of those for different reasons. But of course, carbon has also caused carbon dioxide emissions that we're grappling with and tackling through earth science and of course all the STEM disciplines. And so this is something that you folks get to see in high school textbooks. This is what we're taught as the deep carbon cycle. Plants and animals and lakes and rivers and so on, and the carbon cycles through this. What if I were to tell you that this is just a tiny little part of the planetary carbon cycle? Okay? And this was such a revelation to me that actually there's a much deeper component of the carbon cycle, and actually also the hydrological cycle. Okay? I mentioned yesterday that, 3 times the volume of the oceans exist inside Earth's mantle, and they get degassed through volcanism, and that's how we got our oceans. And similarly, our atmosphere is the result of volcanic degassing, and a lot of that is a small fraction of that is now carbon. Increasingly greater amount because of human activity. And if we look at a cross-section through the Earth, through the Deep Carbon Observatory, I think most people have settled on this idea that the core probably has about 90% of the planet's carbon. The mantle has about 8 to 9%. Continents themselves, you can get carbon pasted onto them or trapped within them, 1.5%. And then you can see that the oceans and atmosphere and the biosphere have a tiny, tiny volume of carbon. Okay, so this is a very simplified perspective of the reservoirs of carbon on Earth. And this is why the Deep Carbon Observatory's logo has the top of the C missing, because we're just looking at 90% or more of the carbon being actually locked up in the Earth's interior. And so this was me, that you can see at the back here, at a modeling and visualization workshop of the Deep Carbon Observatory. This was a very funny story. in about 2008, Bob Hazen, who's at Carnegie, he's not in this picture, but he got a call from the Alfred Sloan Foundation and, just out of the blue, and they casually said, well, Bob, would you like $100 million to do some research? And Bob was like, oh my God, I almost fell off my chair. I was like, yes, of course. And then they called him a week later and they said, look, Bob, it's terrible news. We're very, very sorry. But we can only give you $55 million because of the global financial crisis. So anyway, this launched a 10-year project, and halfway in 2015, they wanted to develop tools to visualize and model carbon cycling on the planet. And it was very funny. I was invited to present G-Plates, this plate tectonic reconstruction software, the open source software. And I was up against representatives from MATLAB, Esri, and all these big companies. And somehow I managed to convince all these wonderful people that actually using the free G-Plates tool was actually really good for them. Not only was it free, but all of the users could use it for free as well. And so then that began a long involvement and funding with them. But yeah, we wanted to understand why we have these swings in climate, the natural variability in climate on the longer tectonic timescales, and we wanted to understand how planetary processes drive these changes. And this is over the last 500 million years. Why do geologists particularly like this time frame? Is that the geological record is far more detailed and robust during this time. And yesterday we talked about the end Permian mass extinction through this huge mantle plume that erupted over Siberia. Now, to give you an idea of how large this volcanic outpouring would be, look at Australia. All of that magenta area is the outline of the Siberian Traps volcanism. Okay, so huge amounts of volcanism over a couple of millions of years, completely almost annihilated life on Earth. And this is what we talk about as being the end Permian mass extinction. And so I'm not going to teach you about all of the elements of the planetary carbon cycle, but I want to at least introduce you to, what some of these might be. So for example, continental rifts, like in East Africa, where Africa is breaking up, seems to be a very significant contributor to the carbon cycle. And hopefully in your PhDs, one of you might actually take up this challenge, because in Africa, you also have a mantle plume underneath one of these rifts, and we don't really understand how much is being contributed from the mantle plume and how much is from the rift itself. So one of you, I'm sure, will fix that for me. The mid-oceanic ridges as well, where that Marie Tharp discovered, hopefully on the globe. You should be able to feel these features in the oceans. They also contribute carbon. The subduction zones, okay, where the tectonic plates sink back into Earth's interior. So think of Mariana's Trench, the Pacific Ring of Fire. The interaction of magmas with buried carbonates, so it could be limestones and reefs and things like that. It could also be coal and other measures, which are actually not carbonate, so I should fix that, but next time. Mantle plumes, which I'll talk a bit about today, and their volcanic products on the surface, which we call large igneous provinces. I'm not going to dwell on this either, but during collisions, we can get these things called ophiolites, and mountain building exposing fresh rock causing silicate weathering, which I will talk about today. So these are kind of the main components of this carbon cycle on the surface. Now, one of the things we were specifically interested in were volcanoes. And these particular volcanoes, we call them arc volcanoes, okay? And what you've got is a tectonic plate and it sinks. It's called subduction. okay, as it sinks, the sediments and water and all these volatiles are driven off, squeezed out like a sponge, and they punch through the Earth's crust and form these volcanoes. And we think about at least 75% of the downgoing carbon is actually returned through the arc volcanoes, and the rest somehow manages to make it back into Earth's interior, making sure that we don't have a runaway greenhouse planetary state. And so, this is how I feel most days. I'm like, oh my God, this is crazy. What am I trying to do here? But what we're trying to do with the plate tectonic reconstructions, hopefully you can see these teethed lines. They represent subduction zones, okay, where the tectonic plates are predicted to be entering Earth's interior again. Okay, that's subduction. And so for many, many decades, people thought, well, if we could just measure the length of the subduction zones through time, that should give us an indication of what we call the subducting carbon flux. How much carbon is entering the mantle. And so the problem, though, was that when we look at the subduction zone lengths and the subducting plate area, how much material is actually entering the subduction zone, there is no, linear relationship. It's very, very strange. So we actually could show that old assumption is, it doesn't work, okay? And so I worked with a very talented student, Madison East, and we were looking at what we call the kinematics, or the convergence rates along the subduction zones. And you see these blue areas. So light blue means not much convergence, and dark blue means there's lots of plate area and volatiles and carbon being taken back into the Earth's interior, and likely also coming back out through the volcanoes. And so you can see how these are mathematical digital models, representations of Earth, and we can interrogate these and try to squeeze more knowledge out of all of this data. Okay, so if we just look up at the top right here, again, this is time, and these are the subduction zone lengths. In between 100 and 150 million years ago, the subduction zone lengths are low compared to some of the other times. So subduction zone lengths themselves are low, but we know it was a greenhouse climate state. So again, that didn't quite make sense with the previous assumptions that, well, your subduction zone length should tell you how much carbon is being released and whatnot. Now, when we look at the subducting plate area instead, so the length multiplied by the convergence rate, we get something very different. Between 150 and about 100 million years ago, we have a huge peak and flux of carbon and material entering the mantle and then coming back through the volcanoes as well. And so that's really important because it explains the greenhouse climate state during this time. And it actually also starts to explain why we have this very strange increase in mantle plume activity. And so we had to think about that, like, well, what the heck is going on? How do we make sense of this? And so Maddie made this really wonderful graphic. This is why it's really useful to have other skills, other than just the science. Art and other things are really, really useful in science. And so essentially what we proposed and what's been shown by the numerical models since is that if you have an acceleration of subduction, okay, more material entering the mantle, well, I think we can all agree that we've got a finite volume in the mantle. So the more material that sinks, guess what? More material rises up. Okay, so you trigger the upwelling and the eruption of these mantle plumes from the edges of these superswells. So, you're starting now to see how we can, make use of these models to explain variations in that climatic state. Okay, so these mantle plumes and these pulses in subduction can generate lots of greenhouse gases naturally on the surface. And so this is a really beautiful schematic. So this is that process that I mentioned, lots of CO2 degassing. Now, CO2 is a greenhouse gas. Climate skeptic friends might disagree, but I would say CO2 is a greenhouse gas, and I agree with Eunice Foote, who figured that out in 1857. So what that does is warm the atmosphere and the surface of our planet. When the surface is warmer, what happens to the hydrological cycle? Can anyone? Yep.
Speed up, maybe?
Exactly. So the hydrological cycle intensifies. You have more evaporation because it's hotter, and therefore you have more rain. So that's one thing. The other thing that happens is because you've got so much CO2 in the atmosphere, your rain picks up the CO2 and dissolves it. And what happens when water, dissolves some CO2? It becomes acidic, right? So you essentially generate a weak carbonic acid, and you generate acid rain, okay? That acid rain, a weakly acidic rain, interacts with silicate rocks. It could be your volcanic rocks and other kinds of silicate rocks. And you generate carbonate and bicarbonate ions that get flushed out to the sea and trapped in sediments. And particularly, you have microorganisms, like foraminifera and plankton, and even reefs, coral reefs, taking the carbonate, sticking it to calcium, and you get calcium carbonate. Okay? So you end up with CO2 that's been in the atmosphere causing warming. You're scrubbing it out of the atmosphere, okay? And you're trapping it into the shells of these microorganisms, and when they die, it falls down to the sea floor and stays there for usually hundreds of millions of years, or tens of millions of years at least. So this is how you cool the planet. This is what I mentioned yesterday, the inbuilt thermoregulation system. If it gets too hot in the atmosphere, the silicate weathering intensifies, you scrub more CO2 out of the atmosphere, and you cool the planet, okay? So you can see how interesting and complex some of these things are. So what we can do is, with the plate tectonic reconstructions, pass them through the climate models, and this is a climate prediction that just highlights precipitation. And so what you can see here is that near the equator, unsurprisingly, you have what we call the equatorial humid belts, right? Really intense areas of precipitation and weathering. So that's where silicate weathering is particularly strong. And so one of the things in earth science and geology, well, we have lots of uncertainties. We don't really know exactly what the geography was, how high the mountains were, and so on. And so we need to run lots of simulations of paleoclimate. The very high resolution climate models that we use today with the IPCC, they usually take about 9 months on the supercomputer across hundreds, probably thousands of CPUs or cores. Okay, and so we just can't afford that for this sort of activity. So we use an intermediate complexity climate code that we've adapted and improved. And so this is what you start with, some kind of high resolution geography. You coarsen it to the resolution of that model, okay, because it can only cope with certain resolutions. Oops, sorry, I'm going to go back. But the problem is when you coarsen it, you actually create problems. So we've got the Atlantic Ocean here and then the Pacific. And of course, at the present, we know that we have the Panama Isthmus, right? This is a land bridge that blocks circulation and exchange between the Pacific and the Atlantic. And so what we developed is a mechanism to skeletonize geography. So red is the land bridges and black is the oceans. And then we can use those skeletons to ensure that we preserve ocean gateways and land bridges. And this is extremely important in climate modeling, right? Land bridges are barriers and ocean gateways allow the through flow of water. Okay, so it's very important to do this, and this was a really useful innovation. We could then also benchmark these intermediate complexity climate models to the present day. Chris mentioned, like, how do we believe any of this? Well, it's a very good question. But our predicted temperature profile from, this is the equator up to the North Pole and to the south. This is the kind of temperature profile that we get in blue, and black is the observed. So given the intermediate complexity nature of this, that we're making lots of compromises, and that rather than spending 9 months on the supercomputer, this can run 3-4 days on a single CPU, that's really useful for us because we can get the details that we need. And of course, as I mentioned, it democratizes access to climate modeling because people can do this on their own laptops. If you're very excited to do this, you could do this on your own laptops. And you saw some of these examples that it gives us lots of things, but we are interested in precipitation that matches our own plate tectonic reconstruction. All right, what's the other uncertainty? We don't really know exactly what the atmospheric CO2 was in deep time. We seem to have a better understanding of what we call the global mean surface temperature. And so you can see that from 250 million years to the present, it's gone up and down. The mean temperature here was about 32 degrees Celsius, and it's gone up and down, and it's actually long-term, it's gone down, and of course, like, it's going back up, which is likely problematic. And so we can run lots of scenarios. All these colored stars means that we're just exploring the parameter space of CO2 values. And then we can see, okay, well, which of those simulations match the global mean surface temperature best? And so we can say, well, this is our favored, our preferred climate model. Okay, so now we've got the climate. But what about the silicate weathering and the mountains? Why won't anyone think of the mountains? And so what had been used for decades is things from this atlas. This is a Russian atlas from Ronov et al. In 1980s. And there's only maybe 2 or 3 people in the world who actually have a physical copy of this atlas. Okay, so when we talk about reproducibility, I've never actually seen the data. I have no idea what it looks like. I haven't even got scanned PDFs of the chapters, so I have no idea, right? So that's what's being used for decades, even to this day, and we're changing that. So the way that we're changing that is we're working with UNESCO and other groups to actually map out where the mountains have been through time. So all these different shades of orange represent the mountain ranges, okay? And they change and they move through time. Okay, so we can see Pangaea, the supercontinent, starts to amalgamate. There's lots of mountain ranges here in the equatorial zone, and then Pangaea starts to break up. Okay, so this is how we're also democratizing that data, because we're actually making it totally transparent and available. Okay, so we can then, from this, compute the area of the mountain ranges, so the total area is in red, through time. Again, time going forward in time in the last, billion years. So we get peaks and troughs in mountain areas. Unsurprisingly, when you've got supercontinents forming, you have lots of mountain building because the continents are colliding. But most importantly, you can also look at the latitudinal bands that these mountains end up in, okay? So depending on what you define as your humid belt, 5, 10, 15 degrees around the equator, you can see that then there's these peaks and troughs as well of the mountains in the humid belts, which is where you have the amplified silicate weathering. And, you know, if we can just visually compare this with the glaciation geological records, okay, we have rocks that tell us there's been glaciers around. So often these rocks, you see these very prominent striations through them because the glaciers have been gouging those rocks, okay? So what we can tell from that record, which is completely independent, is about 300 million years ago when Pangaea was forming and the continents crashing into one another. At 300 million years ago, we had very significant glaciations, and that's also supported by the mountain areas in the equatorial humid belts. But you can say, Sabin, this is just all arm waving. You're just, you know, it's very qualitative. But we can actually do this better. We can put it through what we call carbon cycle models, or carbon box models. And this is what, you know, the state of the art, this is what's being used. This is the Ronov curve, is this dashed line, okay, from say 500 million years to the present, this dashed line. But in, again, the best models, what people use, they say, well, you know, there's some variations there. Let's smooth that out. And we get this very smooth curve. And then they're like, okay, well, you know, just scale it down by 2/3 of the power or whatever. It's like, what? That makes no sense. Like, why? Like, nobody actually explains why. And so instead, what we can do from these sorts of models is we can compare these forcings in the carbon cycle models. And so black is this old curve that people have been using, and colored are all the different scenarios that I can extract from different models, okay? So you can see that I get a lot more detail, again, backed by the data. And I don't really want to dwell on how the carbon cycle is resolved, but there's lots of papers published on this, and, you know, I can point you to that. Okay, so these models allow us to predict atmospheric CO2, okay, which you can see all the way to the present. And the blue dots represent the data, or the best thing we have at the moment anyway. And you can see that some of these models, you know, don't really do a great job. The original model, the black line here, it's pretty flat. It doesn't actually, you know, explain many of these peaks. When it comes to global average temperature, we can also have a look at these different scenarios and how well they match. And so in some of these key times, you can see, for example, this green model does really well, and probably does really quite well overall, okay? But this is the sort of way that we can quantitatively test different paleogeographic reconstructions through time, and actually figure out, okay, well, you know, does any of this make any sense? And what does it mean for paleoclimate and the modeling that we do beyond this? So that's kind of the carbon cycle modeling. This is, and that's all quite fresh. This is all quite new. This is something that is also quite interesting that we're exploring at the moment, which is essentially growing reefs in these sorts of settings. Now, what you've got here at the bottom, you can see a cross-section. This is what we call a rift, or a continent breaking up. Okay, so continents, as you stretch them, they start to be thinned and they start to break up. This is what we have in East Africa. Now, in many, sorry, I just want to restart the animation. In many of these rift settings, you get these, well, these pink areas represent your reefs. Okay, so reefs grow in some of these marine settings. what we're actually arguing here is that the reefs, as they grow, they trap sediments coming from the continents, okay? Sediments are being flushed from the rivers, and if it weren't for the reefs, they would end up here in the rift center. And sometimes we have sedimentary packages that are 5, 10, 20 kilometers thick. Now, the significance of that is if you have 5, 10 or more kilometers of sediment here, you would load the surface, okay, and through this process we call isostasy, okay, you load it, and so it has to sink. As this rift then sinks deeper, it gets hotter down there, okay? So the presence or absence of this thick pile of sediments fundamentally changes the deformation regime and the deformation style in that rift. And what we're actually arguing here is that the biosphere can actually impact tectonic processes. And that's actually, you know, a really interesting and important idea that life itself can modulate tectonic processes themselves. But how does this actually, all of this relate again to the UN Sustainable Development Goals and some of the things that we talked about? And there's so many here. I'm not going to be able to talk about all of them, but let's talk about how the geology, whether it's through silicate weathering and other processes, has been capturing carbon for tens, hundreds of millions of years. And so many of you have heard of carbon capture and storage. You can say liquefy CO2 and pump it into sedimentary rocks. And to be honest with you, if you asked me, 2 years ago, if we should be thinking about carbon capture and storage, I would have said no, don't waste our time, just stop emitting carbon to begin with, right? The problem we are approaching, or probably have exceeded, is the fact that we're now heading towards what we call overshoot scenarios of atmospheric CO2. So even if we stop carbon emissions altogether today, we will need to take carbon out of the atmosphere to try to mitigate the worst effects of climate change. So we've kind of been cornered into making these tough decisions of some geoengineering. And we have to be really careful because these things are often expensive, also not always entirely proven. So it's a tough, we're between a rock and a hard place. Don't mind the geological pun. So we can inject CO2 into sedimentary rocks. The problem with this process is you have to assume that that CO2 in a liquid state will stay there happily forever. And we have this, that does happen, but we can do something better, which is you can get water, mix it with CO2, so you get a CO2-rich brine. And just like the silicate weathering process, you can pump that water through silicate rocks, in this case basalts, volcanic basalts, that have lots of these gas bubbles in them, and this fluid reacts with those pore spaces and creates minerals. Okay? So you turn your CO2 into a solid carbonate mineral, and you capture that forever as a solid. Okay? And so the Deep Carbon Observatory and others have been actually doing this in this program in Iceland called CarbFix, and this is some of their infrastructure where they can actually inject these brines into the Earth's uppermost crust and sequester CO2. And so Iceland, they have a very small population, but they'll be carbon neutral by 2040. okay? There's me and Emily Mason from Cambridge, and this is what some of that looks like. And I thought, you know, this is very cool, but Australia, we're such an ancient continent. We don't have active volcanoes on the mainland. I was so naive, right? I was like, oh, actually, we have very young volcanism, particularly on the east coast of Australia. If we look all the way to the south, these are what we call the neo-volcanic province. Mount Gambier and some of those volcanoes erupted 5,000 years ago. And these volcanoes and these volcanic eruptions are actually documented in the oral traditions of first Australians, right? In geological terms, these are still active. They're classified as dormant, but they could erupt again because we have what we call a hotspot or a waning mantle plume somewhere down here in the Bass Strait. And as Australia has gone northward, it has burnt a trail of volcanism through the Australian tectonic plates. So you can see all these colors, right? And so these are fresh basalts that we can actually use in Eastern Australia to try this if we wanted to capture carbon. Now, we mentioned, I think over dinner, that, you know, all these lights, everything we have running on electricity, it's still about 60% of that is powered by coal. And all of that coal is burnt up in the Hunter Valley, north of Sydney. And so you could presumably, if you wanted to, capture that CO2 and inject it into some of these volcanic rocks. The problem is getting government funding and support to actually do the science. The governments get very excited about these things. For example, another project I'm working on is hydrogen. And it's a similar sort of idea, right? That you can create offshore wind farms, offshore Newcastle, so north of Sydney, and you can replace the coal-fired power plants. That's really good. When you have too much of that renewable energy, you can generate hydrogen, but because hydrogen is such a low-density gas, you need huge volumes. And we don't have the above-ground storage in steel tanks to store that hydrogen. So we need to actually think about geological storage of hydrogen as well. And so the governments, because they don't think about science and they don't seem to care too much, they say, well, you know, here's $25 billion to launch the hydrogen industry. And no one's actually thought about, oh, where are we going to stick the darn thing? Like, where are we going to put the hydrogen, right? And so now we're scrambling to try to actually see, you know, where do we put it? And the key thing is that hydrogen is also highly mobile, okay? So you can't stick it into any kind of rock. And so we're running models trying to find areas on the New South Wales coast where you could potentially inject the hydrogen, but make sure that the hydrogen is covered by these, what we call seals, and multiple seals to make sure that it doesn't escape too quickly. So these are the sorts of things that we're grappling with this science. Now, okay, so what are the challenges in future work that hopefully some of you will tackle for us? So I mentioned already that the spatial resolution in these paleoclimate models at intermediate complexity is quite low. You know, there's a lot of work that needs to be done there, hopefully moving to GPUs and computing on GPUs. We also need to try to understand better, like, what are the paleo elevations. So we often know where a mountain was, but we don't really know how tall it was, right? There are certain geological indicators of what we call paleoaltimetry, but they're very sparse and very difficult to come by. as Chris was alluding to, this is incredibly complex. There's lots of feedbacks here. Just turning on or off vegetation models can have, significant effects to the albedo and therefore your climate state. But of course, you can't model all the species of vegetation and do this really explicitly, because we just can't simulate all the processes in the universe unless, we're ending up in this sort of state like the Matrix. Also, what we touched on yesterday in the questions is that you've got so many uncertainties, okay? Australia, was it at the equator or just slightly south or north? Actually, what's quite interesting, some of this paleomagnetic data that we have, it tells us that the continents in deep time, say more than 500 million years ago, that the continent was, say, 30 degrees away from the equator. But it doesn't tell us if it's in the northern or southern hemisphere, right? So then you need to piece it together by looking at other continents nearby and so on. So it's like a really 5D, 6D puzzle that you have to assemble. So this was me back in 2015, a humble participant of a workshop, and thanks to the DCO, I received quite a lot of funding and support. They were very generous, so Chris will laugh at this because it never really happens, and it's only happened through the Deep Carbon Observatory for me. I put in a proposal, and they said yes, and then they doubled the budget. And they kept doing that. I was like, oh my God, what is going on? And they're like, yes, you need to have a workshop in Sydney and bring all of these people together and make sure that, they have childcare paid for and, all this stuff. It was incredible. So it was really, really, really fantastic. But I think the main point I want to say is that, I started very much like you, thankfully, got to meet Chris, and you've got amazing mentors here, Michelle and others, who really care about you, and we're all invested in your success. And you can all do this. You're currently sitting down in these chairs, but I'm confident and convinced that in just a matter of years, you'll be at the front here, and you'll be running these sorts of big projects. So believe in yourself. Don't let anyone tell you that you can't do something. And again, one of the things that I live by, and I know that Chris taught me this, is that we can do science with kindness, okay? We can do it better. We can be kind to each other, our colleagues, and to the world around us. So thank you. I'll end there, and happy to take any questions.